Hey everyone, this is the IA number 1 physics practice test, and here you're gonna watch your boy Mapoy take this practice test and hopefully score 100. But along the way, I'm gonna explain the answers to each question. And we start with number 1. Which is a vector quantity? So let's think about the definition for vectors and its counterpart scalars. Vectors have magnitude and direction, whereas scalars only have magnitude. So what does the word magnitude mean? It means the value or the number. So all of them have numbers to them, but vectors, like arrows, have direction. So if we think about each of these, it's either you have it or you don't for magnitude. So 3 of these choices are scalars. You either have mass or you don't. There's no direction with mass, and it's the same with time. And now, right now, we're just looking at the distance, or 2 choices, distance and velocity. And one of them has to be a vector, and it's velocity. Some of it you just kind of have to know, but velocity has direction. It tells you how fast and in which direction. Distance only tells you how far you went, not really from which direction and such. A good one to remember is velocity and speed, scalar and vector. So speed and scalar go together, just like velocity and vector go together. V and V, S and S. So that's a good pair to remember. Okay, number 2. A student walks 3 blocks south, 4 blocks west, and 3 blocks north. What is the displacement of the student? So whereas distance talks about how far you went, displacement takes into account direction from start to finish. So let's draw this out. We go 3 blocks south, and then 4 blocks west, and then 3 blocks north. So notice how north and south are in opposite directions. If you forget your directions, I highly suggest a compass. So you draw it. North, south, east, west. So opposite directions like north and south cancel out. So these guys, north and south, cancel out. So overall, from our start to finish, we only moved 4 blocks west. Number 3. What is the total displacement of a student who walks 3 blocks east, 2 blocks north, 1 block west, then 2 blocks south? Alright, now this is a more complicated diagram. So I'm going to do it to the right of this. 3 blocks east. Ooh, that's the wrong direction. This way. 2 blocks north, 1 block west, and then 2 blocks south. Okay. So overall, we started here and we ended here. So we're going to move this way. So that's going east. How many blocks east? So let's do this numerically. We have 3 east, 2 north, 1 west, 2 south. So notice how north and south cancel out because they're opposite directions. And so we're left with 3 east minus 1 west. You go overall 2 blocks east. Choice B. Number 4. Here is a resultant vector, and we're looking for a pair of component forces that produce this resultant force vector. So I want you to pay attention to the arrowhead. So overall, we should be looking at components or pair vectors that show up and to the left, right here, just like in this resultant vector. So up and to the left. So looking at each of these, I'm going to draw the resultant vector. If you look at choice A, it's up and to the right. So a resultant vector would look like this, going up and to the right. So it's not choice A. Choice B, you look at here, it's down and to the left. So it's not choice B either. Choice C is definitely going up, but it looks like it's a combination of somewhere between left and right. And it looks like overall it's going to be this way. So it's not quite that one. D is kind of like the best option. We definitely are going up, and we're definitely going somewhere to the left. So looking at each of our choices is definitely not A, B, or C, so it has to be D. This one's a little more complicated, and it's not something you're going to encounter hardly. But the more common example you're going to see Okay, so number 5 here is going to be the more common type of problem you're going to see when it comes to this. So here we have two pairs of components, force vector components. One's going to the left, the other one's going down. We need to combine these two to find the resultant vector. So pay attention to the arrowheads. We need something that combines both directions. So drawing this out, we need something that goes downward. Oop, Mabi. Okay, this way. So looking at each of our choices, it only has to be choice D. So key thing, pay attention to these arrowheads right here. Follow those directions. Because resultants combine those two. Alright, number 6, here is an example of vector components that we have to calculate ourselves. So vector components, you'll find them on the reference table. X equals A cosine theta, A stands for the vector, and AY equals A sine theta. X is horizontal, and then Y is vertical. So plug and chug. Let's focus on these numbers, 24 Newton force, because that is the vector at the angle of 35 degrees. Sine 35. This one is 24 newtons. Sine of 35 degrees. If you plug in those into the calculator and you solve, you'll get that AX, the horizontal one, is 20 newtons and the other one is about 14 newtons. What's there? Choice D. Number 7, here's another one. We are looking for the vertical component, so that is Y. Oops, I dropped that. Vertical corresponds to Y, so that's sine theta. If you don't remember these equations, they're on the reference table. It kicks the ball with this velocity, the vector, at this angle. So 25 meters per second. Sine 53 degrees. AY is 25 times sine 53, plug and chug. And you'll get that the Y component is about 20 meters per second. You'll get 19.97. It's close enough to 20. Alright, number 8. A girl leaves a history classroom and walks 10 meters north to a drinking fountain. Then she turns and walks 30 meters south to an art classroom. What is the girl's total displacement from the history classroom to the art classroom? 10 meters north and 30 meters south. 10 north and 30 meters south. So these two are opposite directions, so you take the difference, and that is 20 meters going south. And that is choice A. Number 9. Which pair of graphs represents the same motion of an object? So on the left-hand side, we have displacement versus time. On the right side, we have velocity versus time. So we have to make sure we take into account that these are two different types of graphs. So the same motion are going to look differently on these two graphs. So let's go and start identifying each of them. All right, choice A. Here we have a curve on a displacement versus time graph. That's acceleration. Velocity versus time, we see velocities increasing over time, so that's also acceleration. Right off the bat, we got ourselves the answer, but let's hold off on that. Choice B. Here we see someone going from negative displacement back to 0, so going forward, and then continues to keep going forward at the same constant rate. This is constant velocity. And then for B, it's also constant velocity. Okay, so the difference between B, for choice B, why these aren't exactly the same, is that for the displacement versus time graph, this is a positive constant velocity graph because it's going up. You're increasing your displacement away from home as time passes. Whereas velocity versus time graph, this is a negative constant velocity because we're on the negative side of the graph right here. Choice C shows displacement going back to 0 over time, so we're going backwards. So this is a negative constant velocity. Choice C on the velocity versus time graph sees that we're decelerating here, and then we're accelerating over here. So it's not constant at all. Choice D shows, oh geez, what is this? It's like actually a ball being thrown up. So this is both a deceleration and an acceleration. And then for the velocity versus time, this is positive constant. But we already identified right off the bat with choice A that both of these are acceleration graphs for the two different types. All right, number 10. Here we have the graph for speed versus time. And we're looking for the total distance the car traveled during the time interval of 4 to 8 seconds. And we're looking for distance. So on this speed versus time, the slope, which is y, change in y over change in x, speed over time, gets you acceleration. But how do we find distance? How do we find displacement? So the area under the graph is the distance. Okay, and we want it between 4 and 8 seconds. So when I say area on the graph, we're going to take a look and break up this region into shapes. And to be honest, that's not a perfect shape. That's not a perfect triangle. That's not a perfect rectangle either. But we can break it up into those halfway through this interval. Okay, and then area of the triangle. Let's focus on the triangle first. 1/2 base times height. So when you see a velocity versus time or speed versus time graph, taking the speed and multiplying it by time will get you that distance. And that's why we have to use these formulas. It's also a little bit of calculus, but no one needs to know that right now. So the base goes from 4 to 8 seconds. That's on the x-axis. That's 4 seconds. The height is the speed on the y. But we need to focus on the intervals, not the boxes. So we go from 10 here, all the way down to down here in the middle. That's 5. So that's 5 to 10. That's a change in 5 meters per second. So 4 times 5 is 20, and half of that will be 10 meters. So that's just for the triangle up there. Now we got to do the rectangle. We could just do base times height. Again, our base is just 4 seconds, and the height of this goes from 0 to 5, also 5 meters per second. And that's just 20 meters. Now, it wants a total within that interval, so 10 plus 20 will get us 30 meters total for number 10. Okay, number 11. We need the magnitude of the total displacement at the end of the first 6 seconds. So if we're going from 0 to 6, we need to break this up into triangle and rectangle again. So following number 10, we're going to do the same thing here. So again, look at the interval on the axes, not the boxes. The height here is 10. This is 10 overall. 1/2 times 2 times 10 is 10. And then the rectangle. 2 to 6 seconds is 4. Height is 10. This is a total of 40 meters for that segment. Overall, 50 meters traveled total. Number 11. The speedometer in a car does not measure the car's velocity, but it measures speed. If you look at a speedometer on a car, it only tells you the numbers. Definitely the numbers are a lot higher, but you get the image. So speedometer only tells you how fast you're going. That's magnitude, speed. But velocity is the vector, because it needs direction with it, how fast and where. So velocity is a vector quantity and has direction associated with it, whereas speedometers only give you the value. Number 13. Here we have a distance versus time graph. So for distance versus time, the slope represents velocity or speed. So we're looking for the average speed of the cart. We could use the slope formula, or we could just, I guess essentially use the slope formula going from here. Delta y over delta x. And we could see that covers a total of 2 meters over the course of 1 second. And that is choice B. Alright, number 14. A car starting from rest. So keyword rest. Starting from rest. VI is 0 meters per second. Travels a distance of 3.6 meters. Meters is the unit. In 1.8 seconds. So seconds means time. The average speed of the cart is what? So sometimes you'll see this in a reference table, average speed. Average speed typically is distance over time. This is also in the reference table. We're assuming it's a constant velocity because we're not really indicated a real change in speed besides from rest or an acceleration. So we can use this formula. So it's 3.6 meters over a time of 1.8 seconds. The average speed is 2 meters per second. Okay, so it's choice B. Number 15. According to the graph, as time increases, the speed of the cart blank. Alright, so this doesn't even show what's on the y-axis. Okay. Let's just pretend this here is the x-axis is always time typically. And on the y-axis, let's pretend this is distance. So as time increases, the same amount of distance is being traveled. So every 1 second, 10 meters is being covered. Another 10 here, another 10 there, 10 there, so on and so forth. So it's moving at the same rate. So for number 10, moving at same rate. That means the speed here is staying the same. Nothing's changing about the speed. It's not getting faster, it's not getting slower, it's still covering the same distance every time. It's a constant velocity, it's staying the same. Alright, number 16, which paragraphs represent the same motion? So again, we have distance versus time on the left and speed versus time on the right. Keep in mind, once again, that these are not going to represent the same shape, even though these are the same motions with different types of graphs. Alright, so choice A, we could rule out because distance is not changing, whereas speed is changing. Choice B, we see a curve, but the speed is constant on the right graph. That's wrong. C and D, let's just double check. So choice C, here we see the distance is changing exponentially. So we're accelerating whenever we see an exponential curve. But on the right side graph, here we also see speed increasing at the same rate. So that's acceleration also. Choice D, let's keep choice C in mind, but let's also look at choice D. Choice D shows a constant velocity in a negative direction, negative v. And then the right side graph shows an acceleration. So these aren't exactly the same thing. So that's also ruled out. So it's choice C for number 16. Number 17. A runner completed the 100-meter dash in 10 seconds. Her average speed is, so you see this on the reference table, average speed is d over t. 100 meters over 10 seconds equals 10 meters every second. Choice B. Number 18. A car travels a distance of 98 meters in 10 seconds. What is the average speed of the car during this 10-second interval? So once again, 98 meters in 10 seconds. That is 9.8 meters per second. Choice B. Number 19. Alright. Oh, another displacement question. Alright, so here we're looking for the total distance traveled by the object during the first 4 seconds. So we have a speed versus time graph. When talking about distance, we need to think area under the graph or a curve. So here we have a triangle from 0 to 4 seconds. Area of a triangle equals 1/2 base times height. If you don't remember these area formulas, they're also on the reference table. Base of 4 seconds. On the x-axis, the height is on the y. So we go from 0 to 20. That's 20 meters per second. 1/2 times 4 is 2. 2 times 20 is 40 meters. And that's choice C. Alright, number 20. A high-speed train in Japan travels a distance of 300 kilometers in that many seconds. What is the average speed of this train? So key thing, you need to pay attention to the units, kilometers. So 300 kilometers equals 300,000 meters. Because kilometers is big. 1 kilometer is 1,000 meters. So average speed, d over t, 300,000 meters over 3.6 times 10 to the third is 1,000. So it's 3,600 seconds. So this is going to be 83.3 meters per second. If you pick choice B, while you did the math correctly, you need to make sure that kilometers is converted to meters, because the units in our answer choice is meters per second, not kilometers per second. Alright, 21. A student on her way to school walks 4 blocks east, 3 blocks north, and another 4 blocks east, as shown in the diagram. Compared to the distance she walks, the magnitude of her displacement from home is less, greater, or the same. So let's compare each of these values. Distance is the total path. So she walked 4 plus another 3 blocks plus another 4 blocks. And that is 8 plus 3 is 11 blocks. That is her total distance. But displacement, on the other hand, is different. So displacement takes into account direction. So she went 4 east, 3 north, and another 4 east. So she went a total of 8 east plus 4 north. So that makes a triangle in a way. So this is 8. This here is still 3, and we need to figure out what this is, the resultant. Okay, so we need to use Pythagorean Theorem. 8 blocks squared plus 3 blocks squared equals c squared. Alright, so after you do all that math, you should get a displacement of 8.54 meters. So the displacement here is smaller than the distance. So displacement is less than her distance. And this is always the case if you change directions. Displacement typically will never be greater than your distance. It's always smaller or the same, depending on the scenario. Alright. Alright, we're on the very last page, and I did not think it would take this long. I didn't even think I made this many questions in the practice test. But anyway, 22. A golf ball is propelled with an initial velocity of 60 meters per second at 37 degrees above the horizontal. The horizontal component is what? So we need to solve for the x component. Ax equals a cosine theta. So we could just do 60 meters per second times cosine of 37 degrees, solve, and you get about d 48 meters per second. 23. A runner starts from rest. Starting from rest. So vi here is 0 meters per second. Accelerates uniformly to a speed of that. So it accelerates. Look at the units also. So I've seen some of you guys confuse these units. It's not saying acceleration is 8. It's saying the new speed is 8 meters per second. Remember the units. So Vf is 8 meters per second in 4 seconds. Seconds is time. We are looking for the acceleration. They want the value, the magnitude of it, the value of it. So you just calculate it. So if this was a two-part question, make sure you write that equation that you're using. That's the first step. Second step, set up with units. So 8 meters per second equals 0 meters per second plus a times 4 seconds. So that numerical setup is what I need to see for the first point for work. Then you just plug and chug and calculate, and you get that a is equal to 8 divided by 4, and that is 2 meters per second squared. 2 meters per second squared, choice B. Alright, a student walks 40 meters along a hallway that heads due north, then turns and walks 30 meters along another hallway that heads due east. What is the magnitude of the resultant displacement? So heads 40 north, and then 30 east. If you notice, this is almost reminiscent of a 3, 4, 5 triangle, which is basically that, Pythagorean triple. So it's 50 meters is your displacement. Choice C. 25. We are looking for the magnitude of the resultant force. Okay, here we have something that's acting due north and a 40 Newton force acting due east. So the resultant vector will be something like this. How do we calculate it? Again, it might look differently than what you used to, but this is still Pythagorean theorem. Even though the resultant and the component vectors are oriented differently, it's still the same. So if we rearrange these, it's still the same type of scenario. This is 20, this is 40, and our resultant is this way, going in the same direction. So if you just rearrange those vectors, you still get the same sort of looking method, still same looking resultant. So we're using Pythagorean theorem. 20 squared plus 40 squared equals c squared. You'll get that c squared is equal to 2000. Take the square root of that, and you'll get that the resultant vector is equal to 44.7 newtons, because that's the original vector's unit. Okay. Number 26. A roller coaster traveling with an initial speed of 15 meters per second. Okay, so that VI is 15 meters per second. Decelerates uniformly at -7 meters per second squared. So notice how that A is negative because we're decelerating, slowing down. So deceleration means we're slowing down, accelerates means we're speeding up to a full stop. So it's decelerating to a full stop. What does stop mean? Rest. We're not moving. So that VF is 0 meters per second. Approximately how far does the roller coaster travel during its deceleration? So we're looking for D. So reminder, when something is moving, its acceleration is pointing in the opposite direction for it to slow down. So that's only when it slows down. Alright, so we're going to use the equation, kinematic equation on the reference table. So 3-step method, as always, get into the habit of that. VF squared, so VF is 0, equals VI of 15 meters per second, and we square that, plus 2 times negative 7 meters per second squared times distance d. So that's a lot, and I try to crunch it all. So let me show the algebra in another step. So we get 0 equals 225 plus or minus 14d. Now I've seen some of you do this step incorrectly. We gotta make sure we do not combine these terms. 225 does not combine with 14d. Why? Because it has the variable. So we gotta bring in the 14d to the other side. Okay. And you'll get that distance is equal to 16 meters approximately, and that's choice C. Alright, number 17. Sorry. 27. How long will it take an object to move 100 meters? So when they say how long, we gotta think time. We're looking for time. Let me use a different color. How long will it take an object to move 100 meters if the object is traveling with an average speed of 0.5 meters per second? Oh, that's really slow. So when t is in the denominator, a variable's in the denominator, you gotta cross multiply. 0.5 t equals 100, t equals 200 seconds. So long. Oh, sorry. Choice A. I'm almost getting confused looking at 28. Alright. Running out of room here. Alright, number 28. A car initially traveling east with a speed of 5 meters per second is accelerated uniformly at 2 meters per second squared east for 10 seconds. We're looking for the distance the car traveled. So, reminder, both the car's movement and the acceleration are both in the same direction, so we should know it's speeding up. If it's in the opposite direction, it should be one of them's west and it's slowing down. That's just a reminder. But anyway, we're looking for distance. So, let me pause here. Alright, so I felt the need to sort of start over on a new slide for the last 3 questions. And here we're starting with number 28. We're picking up where we left off. So a car initially traveling east with a speed of 5 meters per second. Okay. So initial speed for number 28 is 5 meters per second. It's accelerated uniformly at 2 meters per second squared east for 10 seconds. Okay. We are looking for the distance in this time interval. So we're going to use this equation. Now, think to yourself, why are we using these equations? Why not the others? If you look at your information, we have these variables. And we got to make sure we use the correct equation that lets us solve what we're looking for without having a second missing variable. Okay. So d equals 5 meters per second times 10 seconds plus 1/2 2 meters per second squared times 10 seconds, and that's squared, the time. Okay, I'm going to pause for the intermediate math, or change to a different color. D equals 50 plus 1/2 times 2 times 100 squared. 100 squared is 200, times 2 is 200, divided by 2 is 100. Alright, and we get that D is equal to 150 meters, and that's choice D. Number 29. A rock falls from rest. So it's falling, it's being dropped. It's from rest. So VI is 0 meters per second, because it starts there. Falls a vertical distance of 0.72 meters to the surface of a planet in 0.63 seconds. The magnitude of the acceleration due to gravity on the planet is, so as much as we like to say it's going to be choice D, but it's not. It's not 9.8. That's only 9.8 on Earth, because it's based on Earth's gravity. When you go elsewhere, it's different. So we're actually going to solve for that new acceleration because we're on a different planet now. Okay, so we're going to use this same equation again. But the beauty of this is that because VI is 0, when you multiply anything by 0, it cancels out to 0. So that whole term goes away because it's 0. Okay, so we get 0.72 meters equals 1/2 A times 0.63 seconds squared, and A is equal to 3.63 meters per second squared, and that's choice C. Alright. Number 30. An object falls freely from rest near the surface of Earth. So when they say it's on Earth, that means we think 9.81 this time. So I'm going to do this on the other side of the paper. Falls freely from rest, starts at rest. Now we're on Earth, so we can use 9.81 meters per second squared after having fallen this distance of 4.9 meters. What is the speed after that? So we're looking for VF. We're going to use this equation. We're solving for VF. And then VF is equal to 9.8 meters per second. So that's how fast it is after falling 4.9 meters. And that's choice B. And we've reached the end of this practice test. If you're still hazy on some of those other topics, make sure you go check out those content review videos on 1D kinematics, freefall, and motion graphs. So those are the three main content areas that we're covering on this IA that all are pretty much included in the 1D kinematics unit. So make sure you take a look at that, especially 1D kinematics, guys. A challenge problem awaits you.